about geometric series, remember that the difference between a sequence and series is that the terms are added together. And so we're going to focus on finding the sum of the series. So this goes with lesson 9.5 in your textbook. So I'm just going to give you a simple geometric series. Let's say we had everything be multiplied by a common ratio of 2. Okay, so that's a geometric sequence. So you look like this. Okay. So if we wanted to find the sum of the series up to a certain point, here is what we would be looking at. So let's say we wanted to stop at some point. So basically we have the first term. Remember that you have the first term and the ratio. Okay? So let's say you were trying to find the sum of n terms. Okay? So there's the first term. This is the second term. Okay? The third term would have the first term and the ratio to the second power. Okay? And this would continue. And the nth term, or the last term, would have the first term times the ratio to the n minus 1 power. Notice that all the terms have a1. So if I factored out a1, I would have the following. Which doesn't look that interesting. Now I'm going to do something that you might not think of doing, but you'll see that because of the signs, it actually helps us. So what I'm going to do is I'm going to multiply this by 1 minus r. Now, I know I can't just do that, but I can if I multiply by 1 minus r over 1 minus r, because that's really just like multiplying by 1. So if I do that, then my expression is going to say that I have 1 minus r in the denominator, because there was nothing there before. In the numerator, I have a1 times this giant quantity times the 1 minus r. Now, I want you to look at what happens as I distribute the 1 minus r to each term. So 1 times 1 would be 1. And negative r times 1 would be negative r. 1 times positive r would be positive r. And negative r times r would be negative r squared. 1 times r squared would be positive r squared. Negative r times r squared would be negative r cubed. You can kind of see a pattern here. If we continued this pattern, remember that right before r to the n minus 1 is r to the n minus 2. So if we had multiplied 1 times that, we would get r to the n minus 2. And then if we multiplied negative r times that, we would get negative r to the n minus 1. Then when we go to the last term, we get plus r to the n minus 1. And then we get minus r to the n. Sorry that it overflowed a little bit over here. But you can see that basically all these terms are going to be canceled out by some previous term, okay, except for the first and the last term. So our formula becomes, and this is important to write down because this is the actual formula we're going to be using. So this means if I want to sum up a certain number of terms in a geometric series, I can do it using this formula. All right, so the next problem asks us what is the sum of the geometric series. So in the first one, we're trying to find the sum of how many terms. So first of all, we have to know that 2,916 is what term? A sub what? So we want to look at the rule. Okay? The ratio is 3 and the first term is 4, so the rule looks like 4 times 3 to the n minus 1 power. Okay? And then we have 2,916. So where does that fall in this? So if I take 2,916 and I divide it by 4. See what I get. Sorry, 1 minute. So I get 729 equals 3 to the n minus 1 power. So I basically need to know 3 to what power is 729 so I can compare the exponents here. And I believe it's 3 to the 6th power. So the 6th power has to equal the n minus 1 power, which means n is 7. So that means 2,916 is the 7th term. So I'm finding the sum of the first 7 terms, which is going to be the first term times 1 minus the ratio to the 7th power over 1 minus the ratio. So this is going to be 4 times whatever I get when I do that over negative 2. And I'm actually just going to go ahead and put that whole thing in the calculator, but you need to use parentheses in your appropriate spots to get the right answer, or do it step by step. So you can do 1 minus 3 to the 7th power times 4 and divide that by negative 2. You should get the sum of the first 7 terms is 4,372. And make sure it makes sense. That makes sense with the terms I see listed up there. They could add up to 4,372. For part B, I want to do the same thing, but notice the notation. Okay? Because 0 is at the bottom of our sigma symbol, our first term is actually going to be whatever we get when we plug in 0, which is going to be 3. Because remember, this to the 0 power will be 1, and 3 times 1 will just be 3. Our ratio is going to be negative 1.5. And the amount of terms we're adding up is actually 12. And the reason that is because the 0th term counts. So you can counting 0 as the first term all the way up to 11 and you'll get 12. Or you can do 11 minus 0 is 11 and add 1 back and you'll get 12. So the sum of the first 12 terms is going to be the first term times 1 minus the ratio to the 12th power over 1 minus the ratio. Okay. So again, I'm probably going to put all of this into my calculator. So I'm going to do 1 minus, I'm making sure I put parentheses around the negative 1.5 so I don't mess up that calculation. And times it by 3. And then I'm going to divide it by 1 minus negative 1.5, which is actually 2.5. And so I get negative 154.5 as my sum of the first 12 terms. Okay. Could be negative because the negative ratio is taking it back and forth. All right, so a game show is offering a prize of 1 cent on the first day, 3 cents on the second day, 9 cents on the third day. What is the amount of money earned from this prize in 2 weeks? So our sum is that we got 1 cent the first day, 3 cents the next day, 9 cents the next day, dot, dot, dot. And we want to know what the prize is in 2 weeks. So 2 weeks consists of 14 days. Our first term is 0.01. 1 minus our ratio, notice it's getting multiplied by 3, okay, to the power of n over 1 minus the ratio. So again, I'm going to go ahead and put that into my calculator. And I get something you might find surprising, $23,914.84 for the amount of money you would earn over 2 weeks. It's actually not that surprising, though, because think about it. Once you get to $1, it's going to double to $2. Once you get to $2, it's going to double to 4. And once you get to like $100, the next number is going to be 200. So it's going to start making some drastic increase in the amounts you get per day. All right. To write numbers, repeating numbers, as series. I just want to point out that you could do it this way. We could have 7 plus 7 times 10. So we've accounted for the 7 in the ones place and then the 7 in the tens spot. Plus 7 times 10 squared. Plus 7 times, hold on 1 minute. All right, and then you can account for, let's see, so we've accounted for the ones place, the tens place, the hundreds place, and then we would account for the thousands place like this. So you can see that it's a geometric series if the number is repeating because it's the same first term that we used, but the powers of 10 are accounting for the different places. So if we did this with the 0.8888, okay, same idea. You could start with a number and then you could show that it was repeating. So the way that this would help us, okay, notice that the first one we could add up the sum. The second one we're going to be able to add up the sum also because it's a finite number. It ends at a certain spot. And the third one is going to be a little more difficult, okay, because the 4 has that bar over it. So we're going to think about this as being maybe 0.4. Okay, and then 0.4 times the power of 10 to the negative 1 because we want to move behind the decimal one more spot. So the 0.4 got the 10th spot. The 0.4 times 10 to the negative 1 has the 100th spot. And then this would continue. The difference between this one is that it wouldn't have an end. It would continue forever. But notice what's interesting is even though that sequence continues forever or that series continues forever, we can actually sum it up to just be this one number that we write as 4/10, and then we use that repeating bar on top. So that means that sometimes our infinite numbers repeat, but we're able to write them as one number or find their sum, and other times they're not. So we're going to look at a couple series and see which ones we can find the sum of and which ones we can't. So if we look at the following ones, the first sequence, notice, says 4, 12, 36, 108. So notice that the first term is 4, the ratio is 3, and that the numbers are going to keep getting drastically bigger as we add a term onto the series. So this means if you look at the sum of just the first term, we'd have 4. If you add the next two together, we'd have 4 plus 12, which is 16. We add 3 together, we'd have 4 plus 12 plus 36, which is just going to add 36 to our 16 and make it 52. But notice the difference between 16 and 52 is really large. And then we're only going to start adding on even larger numbers, which is going to make the sum get even drastically different than it was in the step before. But if we look at part B, so we're part A has no sum, okay, because if we kept adding it together, it would just get bigger. But if we look in part B, you can kind of compare this to our horizontal asymptotes on another note. If we look in part B, okay, if we add up what we have so far in the sequence, so we have an 8 plus a 4 is 12, plus 2 is 14, plus 1 is 15. 15 plus a half is 15 and a half. And that plus a 0.25 is like, well, plus a quarter is 15 3/4. Okay, now because the ratio here, so the first term was 8, the ratio here is a half, the next term in the sequence is going to be 1/8. Okay, so it's going to keep going. It's going to get to 1/8, then 1/16, okay, then 1/32. Notice that my sum is going to increase. So let me just add on these couple of things and give you examples of this. So right now I'm at 15 3/4 or 15.75. Then if I add on to that 1/8, my sum becomes, I'm going to list the sums over here so you can see them. 15, so I was at 15 3/4 or 15.75. Now I'm at 15.875. Then if I add on to that 1/16, I get 15.9375. And if I add on to that 1/32, I got 15.96875. If I add on to that 1/64, which would be the next term, I get 15.984375. Notice that the answer is changing, but this is a lot like the horizontal asymptotes we looked at. We're changing our sum slightly with each new term added, but it definitely seems like though it's changing, it's starting to change by smaller and smaller amounts, which makes sense because we're adding smaller and smaller fractions. And it seems like it's just converging towards one number. So if I had to guess, I would say this is getting closer and closer to becoming 16. I don't know if it will ever reach 16 because I keep adding on these smaller and smaller fractions. But the sum of all of those would be something that looked like then 16. So it's kind of like the asymptote situation. We would say the sum is the number that it's getting infinitely close to, you know, like that eventually your calculator would round it to. So part B has a sum. So why does part B have a sum and part A doesn't? So in part A, we couldn't find a sum because we kept adding on drastically larger amounts. So just like that situation with horizontal asymptotes where it didn't have one, we couldn't find a number that the series was adding up to or approaching because it just kept growing infinitely big or infinitely small. Okay? But in part B, we could clearly see that if we kept adding more and more onto the sum, if you look at these numbers, it was approaching just becoming the number 16. Okay? And that's because here, the numbers that we were adding on were getting drastically smaller till it's almost like we're adding nothing. And that has to do with the fact that the ratio is 1/2 versus in part A where the ratio was 3. Okay? So if we had to sum it up, okay, we would say you can find a sum of an infinite geometric series. So you can actually add something up that's infinite if it works like an asymptote. If you can actually see this pattern forming where the numbers start to approach something. And that's only going to occur when the absolute value of the ratio is less than 1. So the ratio could be negative or it can be positive. But you're only going to approach a sum if the absolute value of the ratio is less than 1. Okay? So let's think about what the sum formula used to be before and how this is going to slightly change that. So this was our sum formula before. Okay? And I want you to think about the problem we just did where our ratio was 1/2. So this is just going to become a number, and the A1 is just going to become a number. But look at what's happening inside the parentheses right here. If you're taking something less than 1 and you're raising it to a power, and because you're adding on more and more terms, the n keeps getting bigger and bigger and bigger and bigger and bigger, then eventually if you take 1/2 and you raise it to a really big number power, you're still going to have 1 over 2 to some really large power, which is going to give you 1 over some really big number. So eventually in your series, as you get way out there, you're adding on something that's 1 over some really big number, which is really just getting closer and closer to becoming 0. So this part right here is like it's becoming 0. Okay? So in that parentheses, we have a 1 minus what is basically worth 0, and 1 minus 0 is just worth 1. So if we change that whole quantity to 1, this is the formula we get. So in an infinite geometric series, we would have to have the ratio less than 1, but if it was, we could find the sum of an infinite series by using the first term divided by 1 minus the ratio. Okay? So going back to the example we saw before, in part B, we estimated that the ratio was probably 16 based on the sum was probably 16 based on our pattern. So let's look if that works with the formula. So the formula would have taken the first term, 8, and it would have divided it by 1 minus the ratio, which was 1/2. So it would be 8 divided by 1/2. That's like 8 times the reciprocal of 1/2, which is 16, which is exactly what we got the other way. So instead of having to explore what the numbers approach like we had to do in that big chart, again, they were able to kind of generalize a rule of what's going to happen. All right, so there's a few infinite series here. We're going to decide if they converge or diverge. So converge means they do approach one specific number, like the functions that had a horizontal asymptote in the last unit we studied. And to diverge means they don't. And so again, here in this situation, we narrowed it down to when the ratio is less than 1, they do converge towards something. but when it's greater than 1, they don't. Okay? So if we look at the first series, the first term is negative 5. And notice that to get to each subsequent term, we're multiplying by a half. Because the ratio is half, we're going to say that the series does converge, okay? Meaning you can find a sum of the series, and the sum for that series is going to be the first term divided by 1 minus the ratio. So negative 5 divided by 1/2, which is the same thing as negative 5 times 2 over 1, or negative 10. For part B, the first term of the series is 1/4. The ratio is a negative number, because notice how it's bouncing from negative to positive. Okay? And let's see. To get from 1/4 to 3/8, you would multiply by 3 over 2, and then you would do the same thing again in the next one. So now remember, the negative positive part of the ratio doesn't answer the question of whether it converges or diverges, but the numerical part does. So the fact that it's 3 over 2, which is 1.5, which is bigger than 1, tells me that this diverges, so I cannot find a sum. Okay? Then finally in part C, the first term is going to be what I get when I plug in 0. So we plug in 0, it's just 0.8 to the 0 power, and anything to the 0 power is 1. Oops. And because 0.8 is the thing that's constantly being raised to a new power, the ratio is 0.8. 0.8 is less than 1, so that means this will converge. So to find the sum, I'm going to take the first term, which was 1, over 1 minus the ratio, which is 0.8. So I have 1 divided by 0.2. Okay? And you can actually write this out. Okay? So 0.2 is the same as 2/10 or 1/5. So you can look at it that way, or you can look at it as 1 divided by 0.2, in which you'd have to move that over and that over. Either way, you would end up getting 5. All right, so this is it. Your homework is on the board, so you can start that. And then tomorrow in class, what you're going to do, okay, specifically period 5, you guys are going to finish the unfinished problems on your test, but you're getting a new version of like problems. I'm sorry, but I don't trust everybody. It's nothing personal. It's things that have happened in the past. And then period 2, because it's unfair now that they didn't finish, and they get to do that, I got some feedback from you guys about what the hardest problems were, and definitely that graphing problem came back. So in your class, what I'm going to do is give you a different version of that harder graphing problem and go ahead and let you guys work on that. So be prepared for that tomorrow. Then I will incorporate those problems into your test score. All right. See you guys tomorrow. Bye.